Martin Newton. I'm going to do a maths lesson for you today. Or actually what I could do is, just instead of doing a maths lesson, we could do a thing where I try and do some stand-up comedy. Maths teachers and stand-up comedy, I'm not sure that works. What do you think, folks? Well, I'll give it a go. So what I was thinking about was, it's quite trendy, isn't it, nowadays, to be a geek. So it's trendy to be a maths geek or an IT geek. But then suddenly it becomes a little bit too far and you become a nerd. So what happens when you become a nerd or a geek? Well, I was thinking about numbers. And I was thinking, well, actually, are numbers geeks or nerds? And actually, if you start to think about numbers, I was thinking about numbers, well, there's all sorts of numbers. There's fractions, there's decimals, there's primes, all these sort of things. And I was thinking, what about if they went down to a disco? Yeah, younger people, let me explain disco. It's what you probably call a nightclub. Back in the day, we used to call it a discotheque. Anyway, so we've got all these, fractions going down there. And anybody who knows a little bit about fractions, well, fractions are proper fractions. That's if the numerator is smaller and the denominator is bigger. So that's the number on the top is smaller than the number on. Everybody keeping up with this? Are you okay with this? So some of you are saying not. But anyway, it will get more difficult, I can assure you. But anyway, then not only that. So the proper fractions are walking around the disco and looking all calm and sitting down and just looking very proper. And then you've got the improper fractions coming. Now the improper fractions, they're the other way round. It's the bigger number on the top, so that's the numerator, and the denominator is on the bottom, and that's the smaller number. So these are top-heavy fractions. And well, if I was down a disco, a nightclub, I would be looking out for an improper fraction. I would be looking for a proper fraction. I'd be looking for an improper fraction. Sometimes they're known as vulgar fractions as well. So you see, maths actually, it gets a bit interesting. But not only fractions, there's directed numbers. So the directed numbers are going to be down the disco there. And you're going to get the negative numbers. And they're all going to be stood in a corner together, all the negative numbers. You know, negative 12 and negative 13 and negative 15. And they're going to be saying to one another, oh, God, this place is awful. What a dive this is. And then in come the positive numbers from across here. So in come the positive numbers. Hi lads, what a great night. This is fantastic, isn't it? So, brilliant night here. So, what are we doing? Isn't this good? Brilliant. Look at that. Look at those lights. Oh, it's fantastic. So, there we are. We've got directed numbers. We've got fractions in there. And actually, we've got complex numbers as well. So, complex numbers. A lot of people think complex numbers are very complicated. Well, you're probably right. But complex numbers are where you put two numbers together. So you put an imaginary number together and you put a real number together. So the real numbers are the numbers like just 1, 2.3, pi, any sort of number that you can think of, really, that's a real number. And then you've got imaginary numbers, which are where you take the negative square root of. So that starts to get a little bit complicated. But you have to get a complex number, they have to join together. So you've got the real numbers, they're real, you know, they're walking about the place on a real number, and they're looking for the imaginary numbers, and the imaginary numbers, we don't know where they are because they're all imaginary. And they're looking up into blue sky and blue sky thinking. Then okay, other numbers down at the disco. You've got the squares, well, they're probably the geeks, maybe even the nerds, because squares, it's be there or be square, isn't it? So we've got the square numbers. And then we've got the primes. Well, there's loads of primes, isn't there? Hundreds of primes knocking about the disco. We've got 2, 3, 5, 7, lots of them. And they're all in a prime. Oh, I'm a prime number. I'm here at the disco and I'm gonna boogie on with my 6-pack. Actually, this is a 24-pack. Well, those of you who can remember, it's a party 7. Now, so the primes are there, but there's also perfect numbers. Now, perfect numbers, cool, blimey. Pythagoras, you remember Pythagoras for a squared plus b squared equals c squared. The square on the hypotenuse is equal to the sum of the squares on the other two sides. You remember that, of course you do. Everybody remembers that. Even if they couldn't do it, they remember it probably, but maybe some of you don't, looking at some of your faces. So, yeah, so we've got Pythagoras there. And he found this relationship with right angled triangles. And he found what they were called Pythagorean triples, where it got whole integer values. So it got a 3, 4, 5 triangle, and it had length of 3 sides on what length of 3 units on one, 4 units on the other, and 5 units on the other, and they were whole number values. So they were what are called integer values. And he thought, this is fantastic. I'll look for some more of these. So he found loads more. I think 5, 12, and 13. That one works. And then he found lots more. And then he turned his work to perfect numbers. And he found the first perfect number he found was number 6. Yeah. And what that means is it's the numbers divisible by 6, not including 6. So 1, 2, and 3. Add those together, and that gives you 6. So I thought, oh, I like these perfect numbers. I'm going to have a look for these. So there's these perfect numbers down the disco as well. Oh, I'm perfect. I'm a perfect number. And the next one that he finds, he doesn't have to go too far. He goes to 28 and finds that 28 is a perfect prime. So he's got 1, 2, 14, 4 and 7. Add those together, and that gives you the numbers of that gives you another perfect number. So Pythagoras there, he sits down, pen and paper. So he's there and got his pen and paper out. Well, oh, actually it wouldn't have been pen, would it? About 3,000 years ago. So he's got his slate there and he's scribbling away, and he's looking for the next prime number. And he spends the rest of his life looking, no prime, perfect. He spends the rest of his life looking for this perfect number, and he doesn't manage to find a perfect number. And he dies not finding another perfect number. And, well, hundreds, thousands of years later, and the advent of computers and things, and somebody does find them, and they're very few and far between. I think the next one is 400 and something, the next one is 1,000, I forget what the next ones are, but he spent all his life doing that. So, but he's not the only, I mean, so these perfect numbers, they're knocking about and they're perfect, and everybody's looking at them thinking, God, those numbers are perfect, aren't they? And then there's amicable numbers, and amicable numbers knock about in 2s, and where the divisors of theirs add up to be equal to to one another. So we've got amicable numbers, which are 220 and 284. So we've got amicable numbers knocking about. And then, so they're knocking about in pairs down the disco. And come on, let's go and have a look down here. We'll go and have some shots. So there they are, these amicable numbers. And then they bump into a group of sociable numbers, which are all similar, and they all knock about in packs. You know, it's like a stag night. But anyway, that's me being a bit stupid. But I suppose you could call a disco a function. And functions are quite difficult. But functions, basically, what it is, you have an input over here, and you put something in, and then you have an output over there. So it's like a function machine, and it's a relationship between the two numbers. So that's what a function is. Wow, it's good to be in a relationship when you're in a disco, isn't it? So that's what we've sort of been thinking about there. Now, but functions sometimes are a bit shy, and they find it difficult to integrate. And differentiating between them is also quite difficult. Now, if you get that joke, you are a real geek, yeah? Bordering on nerd, okay? So, what I was sort of thinking, I know this is all a bit ridiculous, and we've had all these sort of, this nonsense in the disco, and of course, I didn't really go down the disco when that happened, just to remark my sanity here. But what I was sort of thinking about was, there was this bloke, well, Pythagoras we heard about in the disco. He spent all his life looking for perfect numbers. And there was a chap called Pierre de Fermat, French mathematician, lived about 300 years ago, and he did lots of theorems, solved things, but there was a thing called Fermat's last theorem. And it's quite a simple little bit of maths. And what it said, quite simple joke, so I'm sure you all get this, it was x to the n plus z to the n equals y to the n, only when x is less than 2. Or it didn't work when x was more than 2. So it worked for Pythagoras' triples. You all got that? Yeah, you're all okay with that bit of maths there? I can repeat it and go through it on the board here if you want, but it's up to you. No? Skip it? Okay. Right, so, well, Fermat, it was called Fermat's last theorem. And Fermat, nobody's really sure whether it was his last theorem that finished him off. But anyway, a mathematician called Andrew Wiles from Cambridge University a few years ago, only about 15, 20 years ago, he decided that he would try and prove Fermat's last theorem. So that just in case there was actually a number up there that disproves the theory. So he set off and he just said to his wife, he said, I'm nipping up into the loft to prove Fermat's last theorem. She said, okay, that's fine. She kept supplying him with meals, you know, and after 7 years he came down again. And he said, yay, I've proved it. In that time he'd grown a very long beard, he hadn't been going to work, and his wife had just been feeding him, and he had the occasional bath, and he solved it. And it was 120 pages long. No use to anybody at that point, but probably will be in about 200 years, or even might be now. And so what he did was, he proved it, and he showed it to the world's press, and they thought, ah, fantastic. All the top mathematicians, only about 5 of them, because there's only about 5 of them, could understand it. Humble people like me couldn't understand it. And he looked at it, they looked at it, and they found a fault. And after being up there for 7 years, they found a fault. So off he went again, yeah. Said, I'm just nipping up to the loft again to my wife, to his wife, not my wife, it was his wife. So off he went into the loft, and after about 18 months he came down and finally proved it. Well,